Hello everyone, welcome back to Z Physics. Today we're going to be talking about this very important curve in our study of X-rays. This curve is known as the characteristics spectrum. Now, how is this curve actually produced? I've written up a little explanation here which might be very helpful by inputting this into your notes. So this curve is produced by electrons striking the target in an X-ray tube. The narrow K lines are actually characteristics of the type of metal in the target. So they're produced by bombarding electrons, which literally remove electrons which are close to the nuclei. So if you imagine that the target is, let's say, right here, the electrons are traveling towards it and they're literally removing some of the electrons. Now, if they remove electrons which are quite close to the nucleus, let's say that the nucleus is here and is equal to 0, let's say if this electron is removed, then a higher state electron will drop down in energy. And when it does, it will release a photon. So a photon is released. I've summarized this over here. Once again, they're produced by the bombarding electrons, which remove electrons close to the nuclei. The gaps are filled with electrons dropping from a higher energy state, and photons are released. So this process is known as Brehmsstrahlung, which comes from German and literally means breaking radiation. This is radiation that is released when the electrons strike the target. Those two characteristic peaks are known as the K lines. Now let's try a question. This is quite a typical exam question. Let's see whether we can use the figure to estimate the maximum accelerating PD for this X-ray tube. Now, the maximum accelerating PD is going to correspond to, of course, the maximum energy. And remember, the maximum energy corresponds to the minimum wavelength. So let me just write this. Maximum energy actually means minimum wavelength. The minimum wavelength, according to this graph, is approximately 2.5 times 10 to the power of minus 11 meters. So lambda minimum is about 2.5 times 10 to the power of minus 11. So what we can do is set the accelerating electrical energy equal to the photon energy. The electrical energy is given by EV, and our photon energy is given by hc divided by lambda. We could directly rearrange for V, and we can say that V, the voltage, will be given by hc, let's write that again, divided by E times lambda. If we were to plug in some numbers, what we're going to get is 6.63 times 10 to the power of minus 34 times the speed of light, which is 3.0 times 10 to the power of 8. And then we're going to be dividing this by E, which is the electron's elementary charge. So that's 1.6 times 10 to the power of minus 19. And we're also going to multiply this by the minimum wavelength, which is 2.5 times 10 to the power of minus 11. And if we put that into a scientific calculator, what we're going to get is 49,725. So it's approximately 50,000 volts, very close to that. So let's just approximate that to approximately 50,000 volts of potential. One final typical question I would like you guys to think about is, how will this graph change if the accelerating PD is increased? Now let's think about it logically. If you increase the PD that's being accelerated, you are increasing EV. So in other words, EV will increase. Now, because of that, the kinetic energy of the electrons that are being accelerated will also go up, and so will their maximum energy. Because of that, the maximum energy of the X-rays will also increase. Now, remember, let me just write in some notes. EV is equal to hc over lambda. So in order for this quantity to increase, lambda must decrease because h times c is actually a constant. Because of that, the shortest wavelength will decrease. And if the shortest wavelength decreases, this graph will be shifted, not entirely, but at least here, it will be shifted towards the right. So let's say it's no longer going to be around 2.5, but it will be somewhere along here. Notice though that the wavelengths of the K lines will remain perfectly unchanged. They only depend on the material. They're a characteristic of the material which is unchanged. So the first peak will still be at the same wavelength, about 4 times 10 to the power minus 11, and the next one will also be at approximately 6 times 10 to the power minus 11 meters. Okay folks, well these were some of the basics behind the X-ray characteristics curve, the K-lines, and what will happen if we were to tweak the accelerating potential. Hopefully this video was useful. If it has been, please consider giving it a like and subscribing. Thank you very much for watching, and I will see you in the next video.